So with that, I want to go ahead and dive into FreeFlyer Familiarization. In today's course, we'll be talking about what FreeFlyer is at an overview level. I'll be going through a few of the capabilities of the software, talking about how the software is used and where it's used in the Reach section, and then talk about some of our related software products. All right, so let's bring it all the way back to the basics. FreeFlyer, it's a computer program, and it's used to solve astrodynamics problems primarily for satellites or spacecraft. So these questions are: where will my satellite be in a couple weeks? With what uncertainty am I going to know that? How often is my satellite in view of the sun over a 1-year period? How often is my satellite in view of a ground station over a 24-hour period? What's the chance that my satellite gets hit by a piece of debris? What's a chance that my satellite will hit another satellite? All these questions are essential to answer for spacecraft satellite operations and things that you can answer with FreeFlyer. FreeFlyer has many functions and interfaces, and we provide a scripting language for the user to define and solve any problem. This is different from a lot of satellite flight dynamics softwares, but it's similar to something like Excel, where we provide functions and interfaces right to the user, right to your fingertips, but we don't actually do it for you. We provide a blank screen scripting interface that I'll show you here in a few minutes that really brings the power of the software to you, the user, to be able to configure the software to use however you like. That can sound a little scary. It's a blank screen. Nobody likes writing a project on a blank page. So we provide hundreds of FreeFlyer scripts to make this much more simple. Let's talk about how you would use the software. We have 3 main use cases. The first is in the design process. So when I'm designing a satellite, I'm studying those mission parameters, refining my requirements, determining budget. That can be fuel budget, cost, like actual dollars budget, lifetime budget, power budget, studying constraints to my mission, such as sunlight time, power, things of that nature. So a lot of this design happens in an educational setting, in a class, but also it's the first step for any actual satellite mission that gets flown. Once we have our design, we then move into an analysis phase. In analysis, we're performing trade studies to model optimal flight plans and contingency scenarios. So what happens if is the question. And with FreeFlyer, you can powerfully answer lots of what ifs very quickly with full control over what you're doing. We provide Monte Carlo capabilities so that you can do these trade studies. You can perform lots of analysis, changing lots of little variables over multiple runs. That's very easy to do in the software. And then contingency scenarios. What's a contingency scenario for a satellite? Getting hit by something, coming down faster than you expected. If the drag profile is maybe different than you expected, how do you work around that? End of life scenarios, things like that. And then finally, once your mission is all the way thought through, designed, and analyzed, FreeFlyer is then used in operations as well, where we're actually integrating the software into the ground system. And so every day on the way up, during flight, and on the way back down, you know where the satellite is, you know where it's going, and you know how to plan maneuvers to avoid debris, stay on your mission, make sure that you're over the places that you're supposed to be for ground contacts, for taking pictures, for taking data at the right time, and that you're not hitting anything along the way. So now I want to dive into FreeFlyer and show you a little bit about how it actually works. We're going to create a very simple mission plan or scenario. Mission plan is the file format that we use. And in that, we're going to create a spacecraft. We're going to look at its initial state. We're going to create a couple of different views of that spacecraft, and then we're going to plot the satellite's height over time. So with that, let me dive into my FreeFlyer software here. So this is FreeFlyer. That you're looking at the home screen right now. This is running on Windows. On my laptop here, it doesn't require a lot of memory or power to use. And I did mention Windows. The full IDE that we're going to be looking at today, the Integrated Development Environment, is offered in Windows, the ability to develop scripts. If you are looking to execute mission plans that you've already written, you can do that in Windows, or you can do it in Linux, which is very popular for many ground systems today. So with that, let's go ahead and create a new mission plan. And this is going to bring up my control screen. In my control screen, this is where I'm going to define the mission sequence and set up the whole mission plan. So on the left-hand side, you can see our object browser. In the middle, you can see our mission sequence. And on the right, you can see script elements that we're going to be able to drag and drop into the mission sequence. On the left-hand side, I'm going to add a spacecraft object. And if I double-click, that brings up the spacecraft object editor. And this is where we're going to define our initial orbit. So you can see my initial orbit is there in red. And here's my orbital parameters, as well as my initial epoch. I'm going to bring us into 2021 here. It is closer to our conference date. And then you'll see that my orbit is defined in Cartesian. I don't think in Cartesian. Some of you on the line are very, very smart. You probably think in Cartesian. I don't. I'm the sales guy. So if I use our drop-down menu, you can see that I have a whole bunch of different element types to choose from. The one that I am most comfortable with for today is Keplerian. So I'm going to click that, and it's going to instantly convert my state from Cartesian to Keplerian elements. So here I'm going to change my SMA, my semi-major axis, to let's say 7,500 kilometers. You might think, whoa, that's really high. This is semi-major axis, not height. So just note that. So there's my LEO orbit there. My eccentricity is near 0, so I've got a circular orbit. We'll just leave it right there. My inclination, I'm going to go ahead and change this to a 65-degree orbit. We'll see that inclination update here. I'm going to leave my other orbital elements right where they are, and we've got our initial state here. Next, you'll see I have attitude, physical properties, and visualization. This is where I can set more initial objects of my spacecraft, properties and methods to figure out exactly how to set it to model my, my spacecraft, my mission. I'm going to leave most of these untouched, but I will go into the physical properties page, and I'm going to change the mass of the spacecraft. Note that this is the dry mass, the dry vehicle mass, to, let's say, 750 kilograms. All right, so I've got my initial state defined. Now I'm going to jump to my propagator. The propagator is how we propagate forward in time where the spacecraft is going to be in position and velocity every step. So I have a bunch of different integrators to choose from. If I click, whoa, it's like a dozen or more integrators built into FreeFlyer available for me for whatever type of analysis I need to use. Now, there's a lot here. So I actually am going to jump into my FreeFlyer help file for more information. If I click help anywhere in the object editor, or if I right click on anything in script, I can easily find a relevant help file page. We're very proud of our help file here at FreeFlyer. We spend a lot of time making the software as well documented and easily understood as possible. This help file is available within the software. It's also available on Google. If you type FreeFlyer in just about anything, you're going to get a great result from our FreeFlyer help file. I'll tab back to me. I know that you're probably Googling right now. I understand. All right, so here I'm going to go to choosing an integrator. And here's all those integrators that we were looking at just right now. So here's every integrator and when you might want to use it, when you might not want to use it, and how fast it is and how accurate it is compared to our most accurate and fastest integrators. So all that information is right there at your fingertips. I'm going to stay on an RK89 for now, but I'm going to change my step size to 60 seconds. Next, I'm going to click on the force model. The force model allows me to easily add or remove forces that go into that propagation that are integrated at every time step. So here I've got the gravitational effects due to Earth included, which is good. I'm in Leo. But because we're in Leo, I'm actually going to increase the accuracy at which we're modeling the Earth's geopotential field. So we're going to do 16 zonals by 16 tesserals to get more accuracy there. You can go up to 200 by 200 or higher depending on the geopotential file that you use, and you can use any geopotential file you want. It's very easy to change in FreeFlyer. And then I'm going to leave atmospheric drag modeled, but I'm going to change from an analytic drag model to a Harris-Priester drag model. And very simple to do in FreeFlyer, and we support multiple of the popular atmospheric density models. You can see I'm modeling the moon as a point mass, as well as the sun. And for LEO, that's probably as good as I need to get. If I was out in GEO or farther, I might add the gravitational effect due to Jupiter or solar radiation pressure. All those are just one-click fixes to make my satellite model more and more accurate for what I need to do. But I'm going to leave it here for right now. Next, let's go to our subsystems. You can see that it's very easy to add tanks, thrusters, sensors, and proximity zones to my spacecraft object. For today, I'm just going to add a sensor object, and I'll click Edit Sensor, and we can see a sensor here. Now, a sensor is a geometric construct, and it's how we model something like an antenna, also how we model something like a camera. So here I've got a cone model. You can see I can choose between a rectangle or define my own. Again, there's a lot of define my own theme in FreeFlyer. We give you the power to model anything you want as accurately as you want. I'm going to set my cone half angle to 10 degrees. I can also look at this in 2D. It's just a cone, but if I was making a custom shape, it's very useful to see. And I'm going to leave it nadir pointing. I could change that over time if needed. All right, so I think my spacecraft is pretty well set up. Now let's put something in this mission sequence. What I'm going to do first is drag in a while loop. And it's going to pre-populate this for me. And it says, while the spacecraft has elapsed for less than 1 day, do stuff. It's a loop. So let's go ahead and load something in the loop, and we're going to load in a freeform. If I double click on a freeform, you'll see that this is the blank screen FreeFlyer scripting interface that we were talking about. Let's go ahead and use that. Before we get started, I'm going to quickly move our freeform over to the side so I can see exactly what's going on in the mission sequence. Really easy to configure your IDE as well as output to whatever you need in FreeFlyer. So let's put something in our freeform. Again, we're going to hit every step that we write every time through this loop. So the first thing we're going to do is step the spacecraft. You can see as I'm typing that FreeFlyer autocomplete provides all the functions, properties, objects, and methods that are available for my given use case. So I'm going to step the spacecraft forward in time, and that'll step at 60 seconds. That's the step size that we set. And then at every step, I'm going to view the spacecraft in 3D. I'm going to map the spacecraft in 2D, just using simple commands here. And then let's do a plot. So using the plot command, in the x-axis, which I write first, I'm going to put the spacecraft's epoch. And in the y-axis, I'll add the height. And if I want to look at what that is, you'll see a tooltip pops up, and it says that it returns the height of the spacecraft above the central body along the vector normal, and it's in kilometers. Okay, so that was really quick, but I've stepped my spacecraft forward in time. I've got a couple of views, and I've got that plot. Very simple to set up. I am not constrained to any sorts of plots that might be useful. I can define any kind of plot that I want. That's a benefit of FreeFlyer. I'm going to hit a syntax check. It's going to check and make sure that I typed everything right. I did. That's good. And then I'm going to hit run. Run is going to launch us into our output screen. And here we can see everything that we asked for. We can see the spacecraft propagating in 3D, in 2D, and we'll see that height. We'll see the height staying pretty constant, but it does take the WGS-84 ellipsoidal nature of the Earth into account as we're propagating forward in time. And we know that it's going to propagate for 1 day, from January 1st to January 2nd. So there's that 1 day. So this is my output window. While I'm here, I can use replay to look at any point that I'm interested in. So I can run it backwards. I can make that go faster or slower. I can set that speed up using that drop down as well. If I hit pause, I can actually go to a specific time as well. So if I'm interested in January 1st at 8 o'clock GMT, UTC, that'll take me to the specific point of time that I'm interested in. And then I could run forward or backwards from there. So just more of the capabilities built into FreeFlyer. And our views and plots are all right on top of each other. You can control how those are displayed as well. And we give you the controls to design your mission plan to work however you need. So that's a very simple mission plan. In just a few minutes, I was able to quickly show how the basics of writing a mission plan works. Let me, while I'm here in FreeFlyer, show you a couple more advanced mission plans to show you the kind of the art of the possible. So let's look at a Constellation mission plan. This mission plan is going to measure the coverage globally of many popular constellations. You can see some of them there. Or we can build our own, and that's what we'll do now. We'll build a custom Walker constellation. Every spacecraft is going to have a nadir sensor half angle of 15 degrees. And then we're going to do a global coverage, and we'll put several thousand points there. And then here we're going to define our Walker constellation. I'm going to do 4 planes of 15 spacecraft. My inclination is going to be at, let's do 50 degrees with an SMA of 7,200 kilometers. And we'll leave the rest there. And I'm going to not perform contact analysis. All right. So I'm going to go ahead and build that Walker constellation with 60 satellites. And it's going to load up and start doing calculations here. You'll see on the left-hand side that I have different colors. And these go to my point group here. And the point group is going to change based on the number of revisits. The color will change for every dot based on the number of revisits by any satellite in the constellation over my analysis period. So you can quickly see bands of coverage starting to form. What I also notice is that because of the maximum inclination of my constellation, I'm not getting any coverage over that 50 or so degrees latitude on both sides. So I very quickly designed a constellation, and now I can see how well it achieves global coverage. So you can see this global coverage metric building over the analysis period. And we can use this for constellation design. You could do it without the visualization. You could change those numbers and look at coverage percentages very quickly. And then I could bring the visualization back in to show prospective customers, things like that. Let's look at one more mission plan while we're here. Let's look at the Lunar Gateway mission plan. Just want to show you something interplanetary while we have the opportunity. This mission plan looks at the Lunar Gateway mission that AI Solutions is supporting, along with a number of other commercial companies and NASA and international partners. The next version, the next space station that will be in this weird orbit around the moon. It's called a near rectilinear halo orbit, and it was designed by a bunch of folks, including people at AI Solutions. And it allows us to be in a maneuver-wise cheap orbit around the moon. And what we're modeling in FreeFlyer here is communications between the TDRS network. You might be able to see those 3 ground stations on Earth and the gateway and bouncing communications from the gateway to what might be a future lunar ground station at Shackleton Crater and the Moon's South Pole. You can see several different viewpoints here, looking all at the same point in time in the same orbit, just in different views. So this shows off a lot of the capabilities of FreeFlyer in terms of coverage and contact, in terms of really cool orbits, and great visualization as well. I'm going to stop this and just very briefly show you what this mission plan looks like, just so you know. We added one spacecraft in our simple example. Here we have a ton of different things in the object browser that enable all that mission to happen. And then the freeform for this mission plan is much more complicated as well. But there's great comments in here, and all the code is relatively easy to understand. If I don't know what anything is, I can just hover over and it will tell me more about what it is. If I'm still confused, I can right click and go to help file, and it'll tell me exactly how to use the property or method or object that I'm interested in. We include this mission plan along with hundreds of others inside FreeFlyer so that you can get up to speed very quickly to solve problems for your mission. And with that, let's leave FreeFlyer for now. And let's talk about FreeFlyer's capabilities. So we're going to cover all the capabilities that you see here. I'm just going to go ahead and dive in. So first, let's talk about propagation, which we talked about a little bit before, but we're answering the question of where will my satellite be in the future if I know where it is now? And with FreeFlyer, as I showed, you can propagate one satellite, two satellites, thousands of satellites, whatever you need to do, FreeFlyer can handle it. You can completely control what forces you're using in that propagation integration model. You can turn those forces on and off. What I didn't show is that you can also add your own forces. You can make the FreeFlyer model as complex and as accurate as you need it to be. Our propagation methods, the ones that I showed you, those 12 integrators, are all verified and validated. And so the results that you use will be accurate. And then finally, we showed Earth-centered inertial and other types of frames, but you can also use relative orbits for rendezvous, proximity operations, and formation flights. So if I know where I am, where I'm going, the next question we'll answer is contact. When will I be able to be in contact with X, where X can be an antenna on the Earth, an antenna on the Moon, an antenna on Pluto, maybe one day. Any other satellite, any other group of satellites, either in or A or B, or in chain contact, a specific region on the Earth. Here we're looking at Canada, so we could use political regions, regions of interest, AOR, whatever you need there. A star, a group of stars. FreeFlyer will be powering James Webb Space Telescope, looking at star groups here in the very near future. And then you can perform general line of sight determination from a spacecraft, or you can model specific sensors. You can see our sensor cones here, and you can model as many sensors on a spacecraft as you need. You can adjust the attitude or in which direction that sensor is looking, both at the initial state, and you can change that over time so that you can model sweeping or any other sun pointing, following a ground track, anything like that. And this is used actively today for analysis as well as operations. With our contact analysis in FreeFlyer, you can account for possible sources of interference and terrain. When I say interference, I mean something like a spacecraft being physically in the way, or the moon or whatever, but also RF interference as well. And then terrain, if you look here in the bottom right-hand side of my screen, I'm looking at a terrain model brought into FreeFlyer where I can model line of sight calculations and use that terrain to adjust for any impingements. So we support many different open standard formats of terrain, and you can quickly and easily bring that in to add accuracy to your model. We can also estimate signal strength, as well as many other COM types of calculations for any given contact using our RF link object. All right, so I know where I am, I know where I'm going, and what I can talk to along the way. What if I need to move? How do I change my satellite's orbit? So we have many different ways to model maneuvering in FreeFlyer. We have our low fidelity modeling or impulsive burn modeling, where I can adjust my direction and magnitude and determine that. Or I can go very high fidelity modeling. Using finite burn modeling, I can model a full propulsion system of my spacecraft with multiple thrusters, multiple tanks, multiple valves, A-set, B-set thrusters, blow-down systems, biprops, whatever you need, you can model it in FreeFlyer. And this is used in operations to specify thruster on times and durations. There are multiple different methods to determine the best maneuver. If I look at, how long am I supposed to fire that thruster, I can use FreeFlyer's built-in targeter to set multiple varies and multiple achieves to figure out how long I need to fire or in what direction. I can also use FreeFlyer's optimization capability. We provide interfaces to 3 libraries built right into FreeFlyer and at no extra cost, where I can optimize towards what's the best use of fuel, what's the best way to stay, to stay in my my mission constrained window the longest. Anything that you need, you can solve with our trajectory optimization in FreeFlyer. So next, figured out where to move. That's good. Am I going to hit anything? Critical and becoming more critical every day, especially in LEO, is how to do this conjunction risk analysis. In FreeFlyer, you can propagate both the satellite and any debris or other satellites to determine the likelihood of conjunction. We give you the ability to bring in the entire catalog from 18th Space, from Celestrak, from Leo Labs, wherever you have data from. We're data agnostic. You can bring it right on into FreeFlyer and propagate the whole catalog very quickly. From there, you can then calculate the time of closest approach, the TCA, the probability of collision, or PC, miss distance, many other values useful for conjunction risk assessment. These functions can also be used for rendezvous and proximity operations. Excuse me. And then finally, the last question is orbit determination. Where is my satellite operationally? In space, how do I know where it is? Orbit determination, if you're one of the many students that are online right now, OD might be a class that's at the graduate level. It's a little scary, I understand, but really it's just statistics. Figuring out if I know that my satellite was here, here, and here, drawing a line to connect those points and figure out what my orbit is. Now the head of orbit determination at FreeFlyer is probably on the line. He would tell me it's more complicated than that, but that's the gist. So with FreeFlyer, we provide multiple different ways to ingest multiple different types of measurements of a satellite position with associated uncertainty or covariance. And then once you bring those in, you can fit a curve to those measurements using a batch least squares, an extended Kalman filter, an unscented Kalman filter, or a square root information filter. Those filters allow you to determine this curve that you see here. And this allows you to accurately estimate the forces acting on a satellite at a given point in time. Again, this is a capability that's built into FreeFlyer. It's an entirely different product line for some of our competitors, and we built it in at no extra cost, and it's verified and validated and ready for you today. So that's all the things you can do with FreeFlyer. How do I show that to people, right? Let's talk about output data first. So I have answers. I can report that data to an output screen. You can see an optimization output here. You can save it to a file. We have several different built-in output formats, both our own as well as industry standard formats for multiple data sets. Or you can do a custom format. Say you have a mission-specific format that somebody put in place in 1972. You can do that in FreeFlyer. If you know how to parse it, if it's a flat file or a binary file, you can create those and read those in FreeFlyer. And then visualization. This is the cool part, right? People like seeing plots, people love seeing visualizations. So in order to have a visually interesting way of depicting the answers to my astrodynamics problems, FreeFlyer allows you to view things in 2D and 3D. We showed that in the demo, but then flexibly control where those visualizations go, what they look like, what part of the screen they're in, and then add in plots. You can see several different situational awareness displays here, where users have customized exactly what FreeFlyer is showing in what parts of the screen. Here we're showing 3D models, 2D star maps, plots, all sorts of things to add visual interest and heads-up capability to our users. And then finally, that's great for the user. They can see data. They can see data in 2D, 3D plots. But a lot of times, especially in operations, you need that data to go to other software products. And FreeFlyer contains many built-in mechanisms for transferring files. We have a TCP/IP socket capability. We can read and write to databases. We also have the ability to execute C# code to supplement our existing built-in functions in FreeFlyer, and that's called extensions. So if there's anything that FreeFlyer can't do, you can add code to make it work. And then we have our powerful runtime API. And the runtime API allows you to call FreeFlyer under the hood of another software in C, C++, C#, Java, MATLAB, and Python. And you can quickly and easily call FreeFlyer and just get the answers, get the visualization, any part of that output that you're looking for. You can do it right from other programs. Our powered by FreeFlyer softwares are what we're going to be featuring in the expo this week. Many of them use the runtime API, so you'll be hearing about them over the next couple of days. For our next section, I want to talk to us a little bit about FreeFlyer Reach. FreeFlyer has been used on over 225 missions. You'll see several of them on the right-hand side there. You can see a lot of different customers, agencies, commercial space, international partners. Many companies and agencies trust FreeFlyer, have been using it since we debuted in 1996. We're celebrating our 25th year at AA Solutions this year. Here we see FreeFlyer powering the Mission Control Center, Houston, in the International Space Station control room at NASA. So you can see FreeFlyer on the big screen there. And that's one major claim to fame is that FreeFlyer is powering all the maneuvers and collision avoidance for the International Space Station every day. We'll also be doing that for Dream Chaser, which you'll hear about this week, and doing flight dynamics for Landsat, SPSS, ORS-5, many missions across Space Force and DARPA. In MEO, FreeFlyer is used on the GPS mission, specifically for LATO, that's Launch Anomaly and T-orbit operations. And sorry, our acronyms there. And so basically, FreeFlyer is used outside of day-to-day operations. So if it's an easy day, you use the built-in software. If anything hard ever happens, you call on FreeFlyer, the real specific software to get the right job done. In GEO, FreeFlyer is used across NOAA's GOES fleet, as well as on many Space Force, Air Force missions, including Eagle. And then outside of GEO, FreeFlyer has been used on MMS, the Magnetospheric Multiscale mission. We'll be doing flight dynamics for James Webb Space Telescope, the replacement to Hubble that's going out to L2 here just a few short months. And then finally, we'll be used and is being used for design today on NASA's Gateway and Orion missions headed back to the moon and beyond. We look at our global reach. Through 2021, FreeFlyer has reached over 60 countries around the world through direct sales, our FreeFlyer University program, our international resellers, and our powered by FreeFlyer other softwares that use FreeFlyer under the hood. You can see some of those here. We are primarily started in the US, have expanded to Europe, and are growing elsewhere. And a lot of that growth is through our FreeFlyer University program. Thousands of students from over 180 universities are actively using FreeFlyer today. And that's been growing exponentially since the program started in 2015. Through FreeFlyer University, we make our engineer-level product available free for educational use around the world. And in that program, AI Solutions partners with aerospace engineering departments and student design teams at universities across the country and across the world. And we provide a 200+ page university guide that helps really reinforce orbital mechanics concepts using the software, not the other way around. And this allows professors to use FreeFlyer in their classrooms for homework problems and for general career prep. And the University Guide, it's written by students for students. Since we started writing the University Guide several years ago, only our interns have exclusively been writing that content. So everything is designed for a university student level to be able to pick up and understand. That University Guide is available online and on HTML and also in PDF format. If you just Google FreeFlyer University Guide, you will find it on our university page about halfway down. Let us know what to add to this guide. We're always looking for new content ideas to make FreeFlyer more and more relevant to university programs. We do offer free licenses to students. We can do node-locked licenses on student computers, as well as network licenses to design labs, or just available for VPN across campus. We also have a student spotlight program. This is a feature on our website that allows students to apply online and show off their work. Every so often we put up a student spotlight that shows off different student projects, how you've been using FreeFlyer to do cool stuff. And that allows you to get more reach for your projects as well. And then finally, our FreeFlyer summer internship program happens every summer. It's how I entered the company and many other members of our FreeFlyer team. We have 3 great interns with us this summer that we're very excited to have aboard. Our FreeFlyer internship season for applications is very short, usually comes online around or after Christmas and is closed by the end of January, and we receive hundreds of applications for these few spots. If you're interested, I highly recommend that you apply and spend time on that application so that you can join us for our internship program. I also wanted to talk to you a little bit about certification. Our certification test allows you to show off your ability to understand and use FreeFlyer. We launched FreeFlyer Certification Level 1 in 2020, and it covers the fundamentals of FreeFlyer. And we're currently planning Level 2. So if you have inputs, let us know what to cover, what a useful Level 2 certification would look like, what features it would show mastery of, and how in depth that Level 2 should go. We're looking for feedback there, so let us know in the chat or reach out to us. Certification is free, and it utilizes content taught in our FreeFlyer Fundamentals training module or our Fundamentals series on YouTube. The test consists of multiple choice and practical examples. And so today, go ahead and get certified. Search FreeFlyer Certification on Google or find the certification page on our website. You can get certified in just a few hours, and you can show it off on LinkedIn. Quickly, want to go over some new features coming to FreeFlyer. This fall, we'll be releasing FreeFlyer 7.7, the next great version of our software. That's going to contain flat plate modeling for solar radiation pressure. You can see Gateway being modeled in flat plates here. We're going to be adding an industry standard drag data format to allow more of our users to get more updated drag data into FreeFlyer more regularly. We're adding Rhinex 3 support. This allows Galileo navigation data processing to happen within FreeFlyer. And then we're modernizing our SGB4 Propagator support as the Space Force continues to modernize their use of SGB4 OMMs and other key parts of propagating the catalog. Looking forward to FreeFlyer 7.8 in 2022. We're adding low thrust optimal control, custom observations and measurement models, and we're doing an update to our vector and coordinate systems. If you have inputs on what you want to see in future versions of FreeFlyer, please let us know in the chat as a question or contact your sales representative. I mentioned powered by FreeFlyer earlier. We have multiple different softwares within the company that are powered by FreeFlyer, and here's 4 of them. The first one is our Meridian Modern Ground System, our streamlined solution for LEO and GEO flight dynamics. Then OBSEM, is our observation data, simulated data that gets streamed to the UDL, the Unified Data Library. Atlas displays is the big screen situational awareness display, highly customized for different missions. And the Deep Space Trajectory Explorer is specifically for interplanetary multi-body trajectories, vibration points, planet-moon systems, things like that, doing that, the design stage of the different stages that we talked about earlier. I could go into all of these, but I don't have to, because we have great programs over the next couple of days talking about all of these things. At 2 p.m. today, we're going to be doing a walkthrough of Meridian operations, and at 3:30 tomorrow, we're going to be talking with the developers of Meridian, talking about how they built it using containers. At 1:30 today, we're going to hear about how FreeFlyer and Opsin are used at SAC-T. At 1 o'clock today, coming up next, we are going to hear about Atlas displays for the Sierra Space Dream Chaser. And at 2:30, we're going to hear about the Deep Space Trajectory Explorer, how it works and what it does. So please stay tuned for all of these great talks. I'm very excited about them. And with that, we have just a few minutes for questions before we start our next panel. I have a really cool video that one of our developers, one of our FreeFlyer experts made for May 4th. It's Star Wars themed. So for every great question that you asked, I will play this amazing video.
Awesome, thanks so much, Michael. We do have a few questions from the audience. First up is, how do we access the recordings of these presentations? That's
a great question. If you go to our YouTube page today, you'll see in the playlist, you'll see a playlist of the 2020 Users Conference. We'll make a similar playlist in the coming weeks for the FreeFlyer Expo summer session, and you'll see those there on our YouTube page. When we get everything up, and it takes us a couple of days to format it all, we will be posting about that on social media, so you'll see it.
Okay. Next question is, can FreeFlyer run in macOS?
Great question. So I talked about Windows and Linux in that presentation and how you would use that. We are currently planning to support macOS in a future release of FreeFlyer. It takes some work to get Mac support, and we have people working on it. I don't think as we speak, because I think they're supposed to be tuned in to this, but they have been working on it today. So we are working to bring that to you.
Great. So the next one is, does FreeFlyer have the ability to model power generation and consumption? For example, given a set of solar panels, the expected power consumption, orbit, and battery capacity, can FreeFlyer help tell us what is the state of charge of the battery at each point in time?
Yeah, so FreeFlyer can model the angle that the solar panel is with respect to the sun, giving the attitude of the spacecraft. And then in FreeFlyer script, you have the ability to then do the math to figure out what that charge looks like. With that scripting capability, you have the power to access all the properties and methods that we have built into FreeFlyer, but you can also add in your own math via trig and a whole bunch of other things in there that you can build on.
Sure, and we do have a solar power sample mission plan that's included with each installation of the software as well.
Good point.
Yeah. So what are the learning resources that are available to start learning FreeFlyer, online or in person?
That's a great question. If you have purchased a copy of FreeFlyer, you have a free day of training available to you. Talk to your manager, and we can get that set up. We have an excellent team of trainers that provide virtual training in all aspects of how to use FreeFlyer. If you are a student, someone looking at FreeFlyer certification or anything like that, we have a lot of different options available to you. The first of which is our FreeFlyer Fundamentals training series on YouTube. That's 90 minutes of content that walks through exactly the basics of FreeFlyer, how to use it. And then additionally, we have a bunch of how-to videos, how to do specific things in FreeFlyer. You can check that out on our how-to channel on YouTube. And then we have the many different sample mission plans and help file built into FreeFlyer.
Okay.
And then finally, I forgot tech support. We have a world-class group of astrodynamics experts who are also experts in FreeFlyer, and they are on the phone and over email available to all of our customers. So if you have any questions about how to do X in FreeFlyer, and you can't find it online or need a fast answer, just email tech support at ai-solutions.com, and they are the real experts.
Okay, great. Next question is, how does licensing the software work? Can I run FreeFlyer in AWS?
Yes, absolutely. So we license FreeFlyer two ways. One is node locked, where it is tied to one specific real or virtual machine. And then we have network license servers that allow you to set up a license server inside your network that can be closed, open, whatever you need. And then you can check out one FreeFlyer license at a time, or two, or whatever you need to individual real or virtual machines. Those machines can be AWS instances. The license server can be AWS, can be on AWS as well. We have, really a lot of flexibility built in, and would encourage you to contact a sales team or your sales account manager for, really looking through those options specific to your use case and finding out, what's the very best price point that we can do that for. Our sales team is happy to work through that with you.
Okay. Next question is, you mentioned the output of data, the reports, plots, and everything. How can you output your visualizations, or can you?
Oh, so I was showing them on the screen, but how can you output them to other people? Good question. So you can save an image from any portion or the whole thing of FreeFlyer, and you can do that from script so that you don't have to, be there to click the save image button. So you can do that programmatically, or you can record the entire thing as a video, and you can do it that way. So a lot of different options. You can also take any report in FreeFlyer or any plot in FreeFlyer, and with just 2 clicks, you can export essentially a CSV of that data for use in other programs.
Okay, and the last one here is, can you model orbits around other planets and the sun, or is it only just the Earth-Moon system?
Good question. I showed a lunar orbit, but that is still the Earth-Moon system. So yes, you can model FreeFlyer around any celestial object. We have built into support for every object in the solar system, every planet. We don't have all 60-something moons of Jupiter built in and ready for you at 1 click, but you can easily bring those in just because we don't want your download size to be gigabytes of information. But you can easily bring in any moon, any body, any asteroid. If you have the SPICE file or the data for it, you can bring it into your model, and you can do full physics-based modeling around any of those objects.